Here we have the basic setup for a titration, pun intended. We've got a burette with some base in it, and we've got an Erlenmeyer flask with an acid. This can be an aqueous acid that's already in solution, or you can weigh it out as a solid and dissolve it in distilled water. As long as you know the mass, it doesn't really matter how much distilled water is in here, because we're going to titrate it. We're interested in the moles. To do this, we can actually switch the acid and the base around. We can put the acid in the burette if we needed to, and the base can be down there. That's pretty arbitrary, but the idea is that one of them is a known and the other one is an unknown, and we're trying to find the equivalence point. So the equivalence point, when you titrate it, you can kind of see that purple indicator telling me here we've got the acid there's more acid in this container than base, so the solution is clear. And if I get to a point where there's more base than acid, and the base is the excess reactant, the solution will turn bright pink. We want to find a point where we are just the faintest color pink possible. There's no limiting or excess reactant, and it's the perfect stoichiometric equivalence point. So you can see we're getting closer, that pink color is sticking around a little longer. And there you can kind of see I even went a little bit too far. One drop is enough to take that farther than it needs to go. But we get a really light pink out of it, and we can measure the volume and say how much of the base did it take to get to this equivalence point. Now we have some information that we can go off of. At the equivalence point, the moles of acid and base are equal. So we know the volume of the base that we just used, and we know how much acid we had in our container. We've got a couple of different possibilities here. One could be we have an unknown base. If we had an unknown base and a known acid, maybe that was a solid, we could take the known acid, figure out the moles of acid. At the equivalence point, it's now equal to the moles of base, and we know the volume of the base, so molarity is moles per liter. So we can take this known and figure out the acid and base stoichiometry, it's a 1-to-1 ratio, and figure out the molarity of the unknown base. So that's one thing we're gonna do. We can also have a known base. Now, if we know the molarity of the base, and we know the volume of the base from the lab experiment, we know the moles of the base, which is going to be equal to the moles of the acid. And if we know the moles of the acid, we can use that to find the molarity of an unknown acid. Because we know the volume, we can measure that out in the lab of the acid in the Erlenmeyer flask, and we know the moles from the stoichiometry here. We can also do the molar mass of an acid. So we can do, moles can give us molarities or molar masses. So if we weigh out our acid on a balance and then titrate it with a known base, we can calculate the moles of the acid. It's going to be equal to the moles of the base. And then just divide grams divided by moles. That could give us the molar mass of an unknown acid. So the point is we have a known, one of these will be a known and one will be an unknown. And then depending on if you need molarities or molar masses, you can do your stoichiometry with that mole calculation. The volumes are going to be done in the lab. That's what the burette is for. You have to get to the equivalence point to find the volume of the titrant that is in the burette, and then you can solve for whichever unknown you have using the unknown of the other substance.